last lecture this week, the Brazilian ICPC summer school, right? This final lecture, we will have some general concepts and some problem discussion. So I guess that's the main topic for today. And as has become usual this week, we will have some of the spillover from yesterday's game theory. Okay, I will add a bit more to complete the exposition, which yesterday was a bit incomplete. So that is our plan for today. So first of all, how did you find yesterday concept? Sorry, contest. Very good. You liked it? Nice. I'm happy about that. I was actually surprised. I don't know if you had some code somewhere, you based that on the internet theory, or you just applied what we saw yesterday. But I was surprised. Like to me, it looks very hard. I think probably it was problem E, the one that looked a lot like NIM, but they have colors in the disks, so you cannot make. You have a NIM heaps, but you are limiting where you can move. Each player has like its own sets of moves. Not the neo-NIM, but the one where there are many disks, and every single disk and every single point has a color. So that's very good. It was solved much more than I expected, so I'm happy about that. That's great. I guess I mentioned the ideas for that one yesterday, but we still did great. I thought it was harder than it was. That one's surprising. Okay, and about the topics, the balance was reasonable. It had, of course, clearly more game theory than usual, but the idea also wasn't that there were 10 problems in theory. Like more than almost all the content. That was not the idea anymore. Okay, good. Any question you want? Yes? Oh yes, thank you. This is actually my favorite Monkey Island t-shirt. You might expect that if you have very good taste, you will clearly notice that this is much superior to yesterday's t-shirt, so it has to be the favorite. At least for now, until I get up again. Yeah. Any other question? Exactly what I was going to ask. Any questions? No? Okay. So, as a reward, or it will be a reward or a punishment. It depends on if you want to know how to solve the problems or if you don't want to know how to solve the problems. Let's discuss. So it's a bit random in that. I guess most of you would like to know how to solve the problem, but I don't know. Anyway, I'd like to mention problem A. Of course, A stands for algorithms, that's obvious, from yesterday's contest, right? Because I think it is very nice. So I will discuss a bit how to solve it, so I hope you can very successfully absolve it after this. I think there were a few things which had ideas from what I talked with a few of you. Some had ideas in the right direction, but the details, the key details were missing, but they were close, at least. So this is a very nice problem. It's a bit surprising. Essentially, we have to construct a tree that contains all of the given words. Right? So in that sense, it's similar to a trie construction, which might be the first thing things in this problem. If you know the trie structure very well, strings, right? Okay, I have to put a lot of strings in a tree. The trie does that. It puts a lot of strings in a tree. So maybe it helps. So for example, we might have we might be given a set of 2 words, 2 random words like tortamalas and malagueta, for example. random words. And we could build a try out of these two, just as one specific example. So how does a try look? Right, you do a path with the word. So you would get, in this case, or that class. So this would be the try for this. So each node ends up representing a prefix. Your words, in this case, with this one being the full word for tamales. And if you do a try for the words, you will have here, because they start with a separate letter, you will have a totally different Malagueta here. And this will be the node for the other. So it is very clear, I think probably from in almost any sample, it is clear that just using the try is not the optimal solution. We want to build the smallest possible tree, because the try makes sure to have every single word appear from the root directly. Right? So the try is the minimal, the smallest, the tree with the minimum possible amount of nodes to contain all the words, but from the start. Right? So it's exactly like it goes through all the prefixes of the words. Right? But here we are allowed to reuse and start at any point. We want the same idea to create a tree that contains all the words, but it's not a requirement to start in the root. So if we have already written tamalas here, we could actually do something also like, oh, I want to start here actually, so that I can write mala root and do something like this. So malagueta. And I will get a smaller tree because then I can cut all of this and I can start using this, and I will avoid 4 letters of initial cost because I just have to add the remaining 5 in this case. Right? Is that clear? So this is the main situation. I think it is very natural to start thinking something like this at least. And from this, you might get the idea like, okay, what is the cost that I am paying? Well, if I do the try solution, which is, okay, it works, this is one solution, you just pay 1 unit of cost everywhere in the whole try, because every single edge creates a new letter and is a new node. So all of the edges will have a weight of 1. But the key observation is that how can I try to model? I mean, I still want to use the try because the try is a very convenient thing. It contains all of the prefixes of all of the words. It is easy to build. It is well known. There are algorithms in try, so it is like a standard idea. Can I do something with the try? So what do I need to model? I need to model the possibility of like this. I already have a word somewhere already written over like por tamalas, and actually I don't even have the full word por tamalas. I will probably have it at some point, but the key here is what I want to extend is not from the full por tamalas word, but from this prefix actually. Right? This is what I am going to extend. So to me, this prefix is the key node in this particular solution. This one I would have to do in order to write the word for tamalas, but for the purposes of getting malaguetas as cheap as possible, I would like to start from here. So I see that every prefix can be useful to create new words. And the observation is, okay, if at some point I have already been able to put this portamala prefix anywhere on the tree, I can expand from there, right? And so in the process of writing malagueta, I will have already written mala. That will already be there, and I only have to extend from that. That idea more or less clear? Okay. So then the key observation is I can then just throw a magic arrow of weight 0 representing represent, oh, if I have already written Portamala somehow, well, I have written Mala somehow. So that has zero cost. I do not have to add a new node to it. And this is the essential idea. Actually, stay on the track, but for every single prefix, throw a zero weight edge towards other prefixes that are suffix of this one, because you can extend from there. Which you probably can build efficiently using Ahobrasic, but I think that for this problem, everything was actually length 10th, and there were only 50 words. So I think for this one, you can pretty much brute force how to build this, and no need to do the efficient automaton construction. But it's actually, it's more or less what you would get if you do the Ahobrasic automaton. You will get these links efficiently. I think you can try every prefix against every prefix and it should be okay. But this is the main idea. And now the observation is that, okay, we have a process where initially we only have the single root tree of the tree that we want to build. And we want to keep adding nodes so that words are constructed. And we will need to have every single prefix of every word at every point, right? So we want to discover or create all of these nodes in the trie somewhere at some point. I mean, the actual ones that we really care about are only the ones that represent full words. But obviously, you will also create all of the prefixes in the process of creating the word. Actually, every substring you will actually create, but those we don't need to encode. That is a good observation. We are not needing to encode every substring because if we reason why this will end up working, if you have two words on the tree somewhere, right, so that they are in the tree where they might not go to the very beginning of the tree, but they will be some segment, let's say. And if two words intersect, right, otherwise, well, we don't care, they don't intersect. If two words intersect, they will have one node, one bottommost node. They will meet at their LCA, let's say, and go upwards, and then one of them will be the one that begins lowest, and the other one's continues a little bit, so perhaps one of the words is like this, and the other one is like this, or the other way, doesn't matter, something like that. So basically, this model correctly represents, it allows me to, let's say, fit or hang or attach this word that starts below after I have already done the other one, right? So this is more or less the like it never happens like you need to combine two words to create a third one, right? So this model will be incorrect. That basically cannot happen. Not with this tree, because of the tree structure of what we are doing. I hope this is enough to understand. If these two happen to meet at the same point, then it actually doesn't matter in which order we do it. Both would give something correct, because when I have the tree at this point, I can basically do them both at the same time, and both orders give the same cost. So actually what we are looking here is for a process of, from a single node, start adding nodes to your visited set as cheaply as possible, but the cost of adding a node basically depends on which nodes you already have visited, because each visited node allows you possibilities of how to reach new nodes. And this is exactly the minimum arborescence problem, right? The directed minimum spanning tree from the root with these costs. This one is also, it has very small bounds, so you can use probably, I guess, the cubic algorithm, right? Which is easier. But it is trickier because you need to reconstruct the full tree. So you actually need to do the reconstruction. But once you reach to this idea, now you know how to solve it. Use the two new algorithm and like contracting cycles. Any question? I hope you believe this works. If not, just look at the drawing very, very intensely like this until you believe it. That's the process. Anyway, you can ask any question. Please.
vos corres el arborescence, and if you run the arborescence, and don't you have these three edges in the tree?
But from Mala, you would, I mean, this is not the full tree, I only showed one example, the full graph. You have to add all of the zeros, right? If we add all of the zeros, like from Mala,
Okay.
Let me remember. Right. Yes. If I am here and I use here, that's the direction I need. Thank you. Yes. Actually, basically, you also have these zeros. You also have these zeros. I was thinking that perhaps you have. I mean, you could also probably fix it by adding ad hoc backward zeros here, because if you've managed to write here this somehow, then you know that you've written this. But you can reason that actually you should already have them, but there is no need to add them because of this. If you reached it by ones, then you're good. If you reach it by some zero, going backwards, you also have like the corresponding ones. And so you can reach those cheaply. So this should be because you have all of these corresponding. But yeah, that might be tricky to reason about. That's the question. Like the way, actually it's good to think how you would reconstruct the tree, right? As that will help understand why it works. And basically the only tricky detail is what is the order in which I will be adding things, right? And basically, if you order the words like from the closest to the root that they start to farthest, you can see that all the additions that you do will end up having this structure. So the actual number of nodes that you are adding matches what the arborescence you're building does. Like I think it should be clear that the arborescence gives one solution, and then because of this drawing argument, you can reason that okay, any solution I have in mind, I look back and forth between these two ideas, and I can actually achieve it. So it's the correct process, right? So yeah, I don't think we need to add those edges, but we could if they were necessary. Like what we need to make sure is that the edges model what we can reach with what cost once we've given the nodes that we have already. So basically, this represents my tree already contains Mala somewhere. So that's for sure is enough information to know that my tree contains Mal. So this kind of zero edges would make sense, right? I could add them and it should not fail here, but because of this, I think they're not necessary. I mean, some of them might be part of the normal algorithm, right? Because perhaps if this is all A's, it's like, okay, it matches itself, so the normal suffix edge like this will actually be that one. No need to additionally add more than that. Any other question? I think the trickiest part here is to actually notice that you should model all of the prefixes. Because to me it was natural to think, oh, perhaps some arborescence where I have one node per word, right, per full word, and that is tricky, that one fails. So there is a jump, a significant leap from saying, okay, one node per word and something like arborescence to noticing, it can be fixed if I put one node per prefix and model like the steps as one single node and not adding a whole word. At least to me, I don't know if anything happens to you, but to me I was stuck at this step with the wrong version of the algorithm, but had to fix it. Any other question? One. we have one more problem on arborescence. I mean, with this one, we now have one more problem. Yet another arborescence problem. Oh, there's a detail I want to mention in general. I mean, I was surprised a bit that, I mean, it's not bad, it's just, I didn't know, though I am surprised, that the algorithm actually runs very fast, like the general process algorithm. You get a good implementation, I mean, it's quite fast actually. So some of these problems that I found, originally the idea was at the same time, in order to make the implementation easier and more efficient, like they have some special constraints, right, for situations. But it seems like using the fully general right from the notebook actually runs unexpectedly fast. And this one, as well as the arborescence problem that appeared in another contest before, only has a 0 and 1 entry, right? And that can actually allow it. Here, in fact, I actually think that we can do the slow edges times nodes implementation, so it wouldn't matter too much. But in general, this will also hold when you contract, right? Cycles. If you have weights 0 or 1 and you do a contraction, the only new weights that appear is a subtraction of previous ones, and it will be non-negative because it will, like your initial choice was the greedy everyone to the best, so the new equivalent cost makes a swaps that increases, so you get non-negative new costs. So basically, you also get 0 ones new costs, right? So everything is 0. And that can simplify the algorithm a lot because your mail double priority, your mail double heaps, right? Your mail double priority heaps could simply be implemented as 2 lists, like 2 linked lists, for example, right? So things having cost 0, things having cost 1, all the time. Whenever you have to merge those, okay, I merge the zeros with the zeros and the 1 with the 1, so it's a constant time linked list matrix. Again, they could even be vectors and you do small and large and push everything. It's also a very easy way to do it with an extra low factor. The concept is you can actually always separate in zeros and 1 because you only have weights zeros and 1. It becomes much more convenient. So I thought that was worth mentioning. Even though the actual one happens to run surprisingly fast, so maybe it's not necessary. Okay. Okay, let's now move on to this part, the game theory part. So let's try to cover some more game theory, and then we move to some general concepts and problem discussion. This last part after game theory will be a bit of a mix. Okay. So just a quick question. Was anybody thinking of something like this yesterday, but they couldn't complete it, or perhaps almost starting to implement, but at the time, or were they very far away? How far away do you think you were from this idea? Like, more or less, instead of saying no. So a few might have said, oh, arborescence, but could not get like the good model at all. Had an intuition for it, I guess, right? Okay. That's the okay, that's interesting. Now you have the good idea and you can code it. So go practice coding. But not now. Now we have the result. Okay. Okay, so back to game theory. Yesterday we saw a recap of some basics, actually like the winning and losing positions, right? Especially for the impartial case, what I call the sieve trick, right? We ended up mentioning loopy games, which is interesting. And then we moved to the sum of games, right? And we mentioned that we might have partisan games, right? And what that distinction mean, right? Because most of the time we have impartial games where the theory is much easier, and that's the nice new case. but we have already seen a few problems appear where the set of moves for one player and the other one differs, right? We will always still keep this convention because it is the standard one. The names of the players are left and right, so these are proper names, and left. This is slightly confusing, but it has some sense. Left is the positive player. I mean, positive scores are good for left. If the score, if the game with value 3 counts how many can be interpreted as how many moves of advantage does left have. So positive is good for left. Because this game we already saw yesterday it was okay. 3 free moves for left, nothing for right. That's like the canonical way to represent game 3. So it is okay. Left can move to a game where 2 moves are still available for left. Right cannot move at all. If right starts, there is no move. Right moves. While negatives would be the other way around. Right? This would be minus 3. Right? So I guess the left and right names stems from the fact that he put left options on the left and right options on the right. But numerically it's reversed with respect to the usual number. So there is some. This will still be our standard notation. Right? So these are things we mentioned yesterday. Okay. So let's be a bit more formal and actually mention a few more important concepts, general useful concepts in these kinds of combinatorial game theory problems, especially game equivalence, game comparison, and the actual comparator, which would be the difference game. So let's go with it. Let's start with the result of a game. We have already been mentioning this. I think it is natural. So that's why even if we don't define them, you can imagine what the result of a game is. It is actually the question who wins, right? So we have been using it already, right? We were computing P and N positions for a lot of games and doing this BP calculation. So how many values are there for the result of a game? Like who wins? I see different numbers. Which is three. Three is an interesting. Six is a super interesting.
Isn't it like if it is 0, there is a tie?
No, we're not having ties. Okay, that's good to mention. Yesterday was the last time we will have loopy games. So our games now to be proper combinatorial games where everything is nice, well defined, and the sum does not get completely out of control. There will be no loops. So all of our graphs will be darks, I guess, with the edges labeled, if you want, with 2 colors. Like these are the left moves and these are the right moves. And some of them might lead to the same node, like if you want to see it as a graph, because this is like an abstract notation that for mathematics and paperwork is awesome, it works very nicely, but computer-wise we like to think everything as graphs and it's basically the same. This will encode the graph, it will be the graph for game 3. Okay, it leads to the graph for game 2, which will lead to the graph for game 1, it will lead to the graph for game 0, and 0 is the name for the terminals, right? A node, the terminal position where we cannot move is called 0. So in terms of graph, this is left can do this move, left can do this move, left can do this move. And there are actually no legal moves for right. So this game very clearly favors right, left very clearly wins this by itself. But in a sum of games, it becomes more complicated. But this thing makes sense to call it 3 because it's 3 free moves at any point for left to try to hold the situation and get the last move, right? And minus 3 will be the same, but in color red. Like only right has. This would actually be like thinking as a graph how it would look this game. But of course, a general game has a mix, right? when we were dealing with impartial games, like, I don't know, the heap nim of size 2, the heap nim of size 1, the heap nim of size 0, that will be exactly the same as out is 0. There is no distinction there. Like plus 0, minus 0, star 0, they are all the 0, the same game. It has no moves. If we want to think of this in terms of parties and games with options, we can, but if we only deal with impartial games, then of course there's no need. It is impractical because all the time we will have, okay, both players can do this move, right? So left and right. Both players can do the move, so left and right, right? So when we only deal with the impartial games, we do not write who can play the move because the rules always say both, right? So it's easier to do a single arrow. But in a sense, it changes the meaning, right? In the general case, that makes the distinction between 3, minus 3, and star 3 would be when both players can do the move. So it is an in heap. It's a very different game than these things. Is that clear? So this is a recap of what were partisan games, which are less common to see in programming competitions. Something we had mentioned yesterday. But then we can ask what is the result of a game. So actually that depends a bit on what do we think of as a game, right? So we should fix that. What do we think of as a game? Which might be ambiguous in general. There are many ways to think what is a game. But in combinatorial game theory, we think of a game as a position, basically, right? And a position in graphs like this. So let's say I have this position. Who moves, left or right? Well, that I only saw someone doing that, and that is the correct answer, basically. It's not defined, right? That's the notion of a game or a position in combinatorial game theory does not include whose turn it is. It is just the position. So that one is still to be defined. So it makes sense to say this game, if left starts such and such thing, if right starts such and such a thing, because it's not defined. You could say, okay, a game to me is the full state of what the position is and whose player's turn it is. For playing a single game, that makes a bit of sense, but when you start adding games, like this is important because in the sum of games, we don't keep track of whose turn it is. It might happen that in the full sum, we have a game like this, and if you look at this at a single game specifically, left is doing many moves in a row in that game, because in the whole sum, left is playing here, and right ignores it to play in a different board of the sum, let's say. Okay. Then left plays again, and right ignores it. Right? Once we have a sum of games, players are not alternating turns anymore within a single game, right? Because they are only alternating turns in the whole sum. Is that clear? So that's why if we are going to use the sum of games all the time, it's not really useful to keep track of whose turn it is, because anyone could be playing now, right? It's always allowed. The game only alternates in a global sense, right? If I have the sum of many games, like only globally, the rule would be left place, right place, left place, right place, right? And you can have local board, it depends on the choice of the player. So with that in mind, a game does not include the notion of whose turn it is. How many results can a game have? I mean, these games do not have scores innate to us. So again, it's only win or lose, there is no tie. And the final outcome is whoever cannot play loses. Okay, yes. So I'm not sure where 3 came from before, but I think it probably had to do with ties. So once we discard ties, the natural option is to say 2, win or lose, but there are actually 4 results, right? Because it's win or lose depending on who starts, right? We could actually write like a matrix of, like actually we could write it as 2 bits if we want. Like what happens if left starts? Left starts. And what happens if right starts? Right? So if left starts, can he win? This is like 0 or 1 possibility. If right starts, can they win? This is like 0 or 1 possibility. So there are 4 combinations. So that is what we will call the result of a game. Who wins, basically, but since it can depend on who starts, because games are partisan now, this will have 4 results. Conventionally, we call them 1, -1, 0, and star. Right? Which are also the game of actual games which have those results. Right? So I wrote them like this because there is sort of a partial ordering relationship to this, right? If we always say that bigger things favor left and smaller things favor right, that is our convention. Right will always prefer. So -1 would be the result. So this would be the possible results of a game, right? If I say the result of G is 1, that means left always wins. If I say no matter who starts. If I say the result is -1, that means right always wins, no matter who starts. If I say 0 for the game, that means the result of the game is whoever starts loses, right? And if I say star, that means the result is whoever starts wins, right? Because those are the results of those specific games, right? Star is the name of the new heap of size 1, so that was the impartial case, and in that case, one single stone, whoever starts wins. The stone. So this is first player win. 0 is empty board, first player obviously loses. But then, because these are partisan games, the new results are, I guess, 1 or -1 for us, that we are used much more to impartial game. Because now it can happen that, okay, it doesn't matter who starts. This game is favorable to the left player, like this, and the left player will always win, no matter who starts, right? Or vice versa. And there is like a partial ordering between these 4 results. Like left would always prefer a game where they always win. I mean, as a result, let's say maybe not a game, but if right has to choose a result, always winning is the best possible result, clearly, right? And always losing is the worst possible result. For left, everything is flipped, right? Left would like a game where they always win, and the worst case scenario is a game where they always lose. But these two are in between, clearly, but they are not comparable among them directly, from the left and right perspective, right? I mean, if you are player left, because left and right are like the proper names, are the fixed identities of the players that will never change, while first player and second player, as you keep playing the game, the terms alternate, so that is like a transitory identity. Not permanent like left and right. It's not encoded in the graph, let's say. So if I say, okay, in this game, what do you prefer, left? Do you prefer that the game is a 0, so it favors the second player, or do you prefer to that it is a star, so it favors the first? And the intuition is like left would not know, because they don't know who they are with. I am the first player or the second. It's quite undefined, especially once you start having a sum of games, right? So those results are not immediately comparable. Okay. So back to this key idea of for game theory. Yes, only 1 second. For game theory, our final goal, our ideal goal, would be if I have many independent games that I can analyze independently, perhaps in a reasonable amount of time or with some theory or whatever, our final goal would be to understand enough information of the separate games to be able to efficiently compute something that allows us to know the result of the whole sum. So that will, we usually want even more, because we want to be able to compose this as long as we want, right? But our main ideal goal of game theory is being able to predict the result of a sum of many games. We develop all of the theory with that in mind. And the result now is which of these 4 situations happens in the full sum.
numbers that are marking?
We are not speaking about this now. That is not the comparison I mean. There is a comparison, and we will see it very soon. But I am not comparing games here. So this is actually, perhaps I should call this result as -1, result as 0, result as star, results as 1, right? I am talking about results here. So this is not the game -1. It is the result of right always wins. Right? A game can have as a result right always wins. I mean, -1 would be the simplest game with that result. So it makes sense to take it as a representative, but this is also the comparison among those games specifically, but here I'm only comparing the results themselves. Right? So things are quite clear. Once we start comparing games, it is more complicated, but that's what I want to mention. Okay. Any other question? And actually, this was the output in for example, problem Sapinius, right? It was actually, you had to give the output in the perhaps more simple notation of who wins if left starts, who wins if right starts, but those 2x2 combinations encode one of these 4 cases. Like always left, always right, the one who goes second, the one who goes first. So the 4 combinations. Okay. So this leads us to think of the notion of equivalence of games, which even if you haven't thought of this formally in the way I will define it now, you are familiar with games being equivalent in the impartial case, at least, because equivalence is nice and solved in a sense in the impartial case. Again, it's the NIM theory, the MEX theory that we usually do. For a game, you compute all the MEX values, so you get this Blandy number, the final number of what it is equivalent to. So for impartial games, everyone will be in the sense that I will precisely define now, and even in the context of partisan games, so the definition is still the same. Impartial games are each of them equivalent to one single in heap, and that is the but more generally, we can define that two games, the equivalence relations between two games. So we can say, let's just say A and B. We can define A being equivalent to B, which, since we almost always only care about the equivalence, we happen to use the equal. Almost all game theory material simply uses the equal notation for equivalent, right? And on the few cases where we care about the shape of the graph, and we are trying to say they are the same graph, like the same actual game with identical graphs, they use three lines, right, which might be flipped. But this is because this is the one we use all the time. We don't actually care about the game. We end up only caring about the equivalence relations. So we say that A equals B, so A is equivalent to B, but we use this notation. When for every single game C, so this should be over all games, A is equivalent to B if and only if by definition. For any game at all, A plus C has the same result as B plus C. So this is very formal notation, but what does it mean? A and B can be exchanged in any sum of games. For the purposes of having sum of many games and computing final outcomes of the sum, A and B are completely indistinguishable. They will swap in one with the other, will never change the result of a sum. So if I have a sum of 1 million games and one of them is A, I can swap it with B and the full result will not change. Okay, that is the definition. So this is an extremely strong property, right? Right now, I guess we wouldn't even know how to start proving that two games are equivalent. Right? It's impossible. I would have to imagine every possible game that exists in the universe and the sum, right? And what's going on in the sum and justify that the result does not change. So very specific in a sense, something very magical and specific has to happen to be able to justify that two games are equivalent, right? But this is what it means. Right? Is it clear? And actually, if you think about how you've been using all of this in the impartial case, well, that is the meaning in the impartial case. I mean, because you know that there's the theorem that the sum of many games is solved by taking the XOR, and if it is non-zero, it is first player wins, otherwise it is second player wins. So the only thing that matters in the sum for the impartial case of this is the XOR of the numbers, and so if they have the same XOR, they will be equivalent because swapping will never change that. Right? So in that specific case, we understand it. But it's actually a very nice criterion of how to know that two games are equivalent, and that is sort of amazing. And it is to look at the difference game. So if we have a game, right, we have some game that has some left options, that has some right options. This is like, there may be many options, but this is like the generic, okay, many options looking like L, many options looking like R. We can define the negative of a game, which is just swapping the roles. In general, it would be if it is a chessboard and left is placed with the white pieces and right placed with the black pieces, it is swapping colors. Now the white pieces become black and the black pieces become red. So the roles are exchanged. That is the definition of the negative of a game. You flip their roles. So if the rules in the graph form, you flip the colors literally, or the letter. You say all that were left moves are now right moves, and all that were right moves are now left moves. Right? In this left options, right options notation, what happens is that you flip them, and also while flipping, every single option by itself is negated, right? Because you don't only flip here one step, but it's like a recursive all of the way change where every option is flipped. Okay. If you have like the full graph, you can just swap colors, but if you have this notation, it's more like a recursion. But regardless of the definition and this idea that you swap and negate, we can see in specific example like this is 3 and minus 3, which is the same with the roles exchange, and it's like flipping side. The meaning is just swap the colors. Right?
A question.
Yes.
If you have like the graph, for example, like 3, 2, 1, 0, then you
This one, yeah. Yes.
then you like negate all of the numbers and switch the arrows like from minus 3 to minus.
This is the negative of this one. This is an example. Yeah.
Like so you take the, for example.
And actually node by node, that is what we have 3 and minus 3, 2 and minus 2. This is a perfect example.
Okay, so the arrows stay the same direction. Like
Yeah, the arrows do not change direction, they only change color. Right? You flip the color of the arrows, not the direction. So yes, the negative of a game means playing the same game, but you reversed the roles. Like if one player, the rules say they can only move to even positions. And, for example, left can only move to even positions, and right can only move to odd positions. Whichever game it is, and there are numbers and something. Then in the negative, it is the same game, but the rule now says right, well, the other way around. Like in this one was even, so now left would be odd and right would be even. Which in terms of abstract graph, it's like flipping the colors. In terms of this notation, exchanging the roles is like, okay, we have the opposite set of moves, and also recursively each move is now the opposite of the way. So why is this useful to think of the game negative? Actually, first as an exercise, what would be negative star or negative star 3, like the negative of an im heaps? So if I flip the roles in an im heaps itself, yes, of course, because there is no distinction in those games between players. So swapping their roles of who is left and who is right, of course, changes nothing. Right? This is an example. This would be star 2. If I flip the colors, well, I mean, right moves from up to down and vice versa, but it doesn't change the situation. Right? And I think you already know that, right? Because if this is negated on the left, so if I put it positive on the right, it would say star plus star is 0. If you know that is is true because the sum is actually the XOR in that case. And start 3 plus start 3 would be 0, which you actually know it is true. So it's starting to look like, oh, very nice properties appear and work, and they do work. All of those do work. This is like a group. So that is why the negative game is so useful. You can actually argue that you can do, well, A minus B is simply A. It's a sum of two games, right? This is the same as A, and do the game sum with the negative of B, right? This is just notation. When I subtract, it is adding the opposite, and the opposite was defined like this, so it's still well defined. But the extremely powerful theorem is that looking at the result of the difference game, this will be the difference game between A and B, just play A plus the negative of B. If you look at the result of the negative game, that is the comparator, basically. That compares A with B, right? And the two games are equivalent if and only if, when you play the difference game, it is a second player win. Right? So we now have a very effective criterion to actually, like, we have an algorithm which checks only finite things instead of the universe of all the games that possibly can exist, which is infinite and unimaginable. Now I have to check only a finite number of things. I take my game A, I play the sum with B negative, and I do backtracking if I want. I analyze that game, but it is one specific game. If the result is, okay, no matter who starts, the second player wins, the two games are equivalent. And if not, they are not equivalent. This is an extremely powerful result. This will be false in the Nisser case, and that is why the other case, the Nisser case, was completely broken. You have almost no theory, because this is the base for all of the theory working out nicely in the end. Okay, and this follows from the key idea of playing mirror, right? You can actually argue very simply that for one specific game, like the inverse is actually a correct inverse. It makes sense to call it the negative. Because if you analyze this specific game, a copy of the game with itself negative, it is clearly a second player win, right? Why? Because if you have two copies G and the same game with the color flip, you have a simple winning strategy as the second player, regardless of the colors and who you are. Just copy what the other one does. If your opponent moves in G, well, minus G is the same with color reverse. So maybe the opponent moved a white piece here, so now it is your turn, and you are the black pieces. Well, then you have the option to do the exactly same reverse mirror move with the black pieces there, and vice versa. You just keep copying, and you will not run out of moves. Right? Is that clear? It's analogous. In the impartial case, we don't have to argue, well, the colors are reversed, but it's the same idea. That's why in the impartial case, a game plus itself immediately you can copy. Here, you can copy if you reverse the colors, right? If you do 3 plus 3, you cannot copy, like, okay, left makes a move, and now you cannot, that's right, because the rule says that you cannot, right? But if you have flip the color, well, you will be able to copy. So this is clear. A game minus itself is a 0, okay? And then this is basically enough to deduce that in general, this powerful result that two games are equivalent, right? I mean, if two games are equivalent, they will have the same result, because you put 0 here, like the empty game, and they have to have the same result. It is written right here. But having being equivalent is much more powerful than having the same result. I mean, there are only 4 results possible for a game, and equivalent classes of the sum, it's completely out of control. It's a super complicated set of possibilities. But for the specific case of the result 0, that is second player win, well, that one is exclusive. That result is reserved for the actual 0 game, the equivalence class of the 0 game. Right? So a game is equivalent to 0 if and only if it is a second player win. Just as we are familiar with the impartial case, that still holds in the full partisan case. Why is that? Well, because almost by the same argument as this, there is another strategic argument. If you know that a certain game has a result of 0, then you can add it or remove it in any sum of games, whichever C you like, and it will not change the result. The other way around. So, putting or removing a game which is a second player win cannot change the final result of the game. We mentioned this briefly yesterday, because it's similar to the mirror argument. If you have whoever has a winning strategy in C can use it if you also have a game here that is a second player win and still win, because they ignore that game and play the winning strategy in C, and they will never run out of moves in C because we are assuming they have winning strategy, so the opponent at some point will eventually come here, and then we just apply the second player win here, right? We use the two strategies in parallel, and in both games in parallel we are guaranteed to not run out of moves. So in the whole situation, the opponent will run out. So that justifies, okay, whoever has winning strategy here, given who starts and everything, well, exactly the same player will have here. They just have to do both at the same time. It actually works. Okay? So this justifies this, which basically means G equals 0 in equivalence terms. This is extremely powerful. Now we have an effective criteria for checking equivalence. So inside equivalence, if and only if the subtraction gain is 0, right? It follows from these two things, right? Because if two games are equivalent, well, A minus B should be equivalent to B minus B. And this one, we already know is equivalent to 0, so A minus B should be equivalent to 0, and that we can check with the other result. Okay? So this is this is basically the main result I skipped yesterday to focus on the calculations and how to compute results. But this is a very general in theory idea and powerful that is worth mentioning. And you probably already knew that concept from impartial games, and here it is slightly more difficult because you have to be careful on where you put plus and where you put minus. If you only deal with impartial games, they are all their own inverses, right? So you can put plus, minus anywhere, and it works because it has XOR behavior, basically. Actually, you can think of it the other way around. Because of this general concept, they will need to have XOR behavior in the end. So the XOR behavior of impartial games arises because in general it is a group, and those elements are the specific ones that happen to be their own inverses. So if you only limit to those, it has to be XOR in camouflage. You can prove that it's forced by math. Okay. Is this more or less clear? So as a one specific example to show that this is a general, very useful principle in game theory, we can use it to prove something that we might conjecture. And I guess one thing that I really like of game theory is that it has all of the time this interesting quality that you are making proofs of very abstract mathematical sets, and games allow you to model values and extremely complicated mathematical structure. But the proofs, the way you end up proving things due to this kind of theory, end up being, oh, all I have to do is check that in this very specific, concrete, one single game, who wins. And if I check that, now I can deduce a property about any sum of any game, right? This back and forth between playing one specific game and proving something very general is something I like a lot. And it stems mostly from these results. This is a key place where it's. We can apply that to the Sapinios game, actually, to prove formally something that we might just conjecture intuitively. Like by playing the game, you might have the conjecture at some point that, okay, whichever position you have in that game doesn't matter. I could have the conjecture, okay, I believe, because it makes sense more or less, I have that intuition, and also I did a few examples and found no counterexample. I believe that if you add extra space at both ends, like this is extra space, this circle will be okay. I can add it or remove it. The original position will be okay. if I add or remove one extra space at the same time in both ends, right? It won't change the game because I gave both players like one extra move. That would be my intuition, right? I mean, it's not completely obvious because perhaps that interferes with the way they cross or something, but I might have this conjecture. Well, I want to prove it. What is it that I would like to prove? I actually would like to prove that this game, let's now do the extra drawing. I want to prove that this game up there and this game down here are equivalent. So if I call this one A and I call this one B, I want to prove that A is equivalent to B, that A equals B. In any sum, I am trying to prove that in any sum of games, I can actually replace this with this, or the other way around, and it won't change the result. That's a detail that I do not need to care about. Which is very nice, because if I prove it, it will immediately tell me that the table that I would like to compute of values will only depend on the difference, that delta that I mentioned yesterday. This will immediately correctly prove it, not only just be my intuition. And how do we prove that two games are equivalent? We just saw it, we need to just play the difference game and check that it is a second player game. So here, in this specific case, we do the difference game. So this is B. What is minus B? Minus B would be the same game with the role reversed. I mean, I could actually swap the rules and say that here, this player now is the one that goes to the left and that one to the right, but that leaves me with inconsistent global rules, like sometimes left goes to the right and sometimes left goes to the left, which will make me more confused. So it's better to always keep the rule that left is the player that goes that way and have the one pointing there. So the negative games I can get by just flipping the board, basically, right? So right is the one that started and has all of this going to move. So if I am sweeping their roles, now left is the one at that situation, and right will be here. Is it clear that these two are the same game with the colors reversed? Right. In order to, because it is much easier to globally keep the rule that left is the one that goes that way. And I mean, I could also have done this, which is more faithful to the definition. Right? This is the original game. Left is sitting here and pushing the sapinios, and right is sitting here and pushing the sapinios. Okay, the negative game is the same, but I flip the letters. Right? I could do that, but I want left to always be sitting here because that's easier to see, so I just flip. This is clearly the same. Right? This is the original one, this is the original. So I can forget for now about B. I actually want to play this particular sum and check who wins. Well, that I can do for this specific game and verify, okay, if I did the backtrack in all the possibilities, it is a second player win, so this one is equivalent to it. But we can do it like in general. If I have one Sapinios game, G, which stands for A, let's actually call it A. Then the other one would be minus A, the game reversed, like this, and the two extra spaces. And we want to argue that this specific game is a second player win. Right? That is something that we can more or less reasonably do, and it's at least possible to prove and quite reasonable, which is, to me, it feels immediately much easier than proving in this. Among all games, it is equivalent to add or remove space. That feels like this is a property of all games, so it's very hard because I have to analyze all possible games. This is something about one specific, very concrete game, so it's easier to analyze. To me, that is like the bigger, powerful part of the theory. And when you analyze this particular game, you can give a concrete constructive strategy of how to win as a second player, and that convinces the proof that this was actually equivalent. What is your strategy? I guess you can, I mean, you have to do a little adjustment, but what would be the main part of the strategy, the main idea? Right, to again use that very general pattern of just mirror the other player. So, I want to win as a second player. Well, I wait, and whatever, if they play in this part A, I copy here. If they play in this part here, I copy here. So, in my situation, if one player moves like that, okay, it means that I was the other one and I copy it here, right, and so on. And I will still have always these copies. So I will not run out of moves like that. My opponent at some point will need to invade, let's say, this extra space because that's the only thing stopping it from being the normal games. So I can, so it's like this, skips me, doing this strategy skips me ahead, straight to the point where we had two equivalent games here, well, not equivalent, reverse, A and minus A. And just after this step, my opponent has used one of the spaces. By symmetry, let's just assume this is the one that it was, so that means that I am left, but if I were right, it would be exactly the same in the other direction. So that gives me only two possibilities. The last move was a jump, or the last move was a non-jump, let's say. Right? If it was a jump, my player was here, and then I have empty spaces. Let's do it a bit. This is the original game, already moved, copy, with the extra space. So they did a jump, so they must have jumped over my Sapinia, so this is what I have, and here is extra space, and the extra space over. But because right before the jump, these two were opposite, right? That means that the actual state of this game is like this, a situation opposite. And they were exactly the same, and this has been jumped. Well, it is very clear that I win this game. All I have to do is push once, and the opponent has won. An end of proof of this case. The only remaining case to check is if it was not a jump, and well, it is very simple. If it was not a jump, that's the final moment when my opponent has to move away, well, somewhere, but not here, because that's where my opponent was before, is my Sapinia, and the extra space. And then in the original position, it is the same reverse, so right before, their Sapinia was, mine was blocked here, and theirs was at the reverse position from here. So it is my turn, these two are blocked, and if you check, these have to be flipped, so whatever space my opponent has here, I have here plus one because of the extra, so I am winning. I just do the moves and I win the race to the end. Well, I lose the race, which is what I want, right? I still have moves. So that's all we have to check. This completes the proof, right? The difference games is a second player game, so these two things are equivalent. Right, so it is quite powerful because now we know that only the difference, we can add or remove extra space, the same amount for every player, and we can those only analyze positions in terms of their deltas. I started yesterday saying, okay, you might conjecture this, right? Well, you might, but you would like to even better prove it, and there is a short way to prove it, and it is to use this difference game criteria. Is it clear? I think this is the main reason why the general theory ends up being so rich and so powerful. That you have this difference game to yes.
How you win, where the last move was to jump over.
Okay, if the last move was to jump over, the state just before that had to look like this. I was here, my opponent was here, and here was the space where they jumped. Right, that had to be the case. So that allows me to deduce what was the state on the other one. Necessarily it was the same, but on the other end because it's flipped, right? So now I know the full game, and it is one specific game. So my opponent has just jumped, and here I have at least one move, even if this was empty, which I actually know that I have at least two moves. The empty space from where they jumped, and the other one that I added. So I have at least two moves. I can do one, and in the other one, all right, I skipped, yeah, sorry, my bad thing. I misread this and I thought this was blocked, this is not blocked. Thank you. So I So you have to be slightly more careful. Thank you, but still, it's only analyzing this specific case. Let's call X whatever extra space is here. Well, I push one move, my opponent will push one move, and what's the situation? They have X extra space, and I have X extra space plus one. Same argument as on the right. Actually, we got back to the same situation indirectly. I still win. Again, we have to do this analysis. Yes, it's still simple, but I skipped it. Yes, my bad. I thought this was blocked. Thank you. So the powerful thing is that you can deduce things about all of the games by playing one specific ones. And many times the strategy to justify it is something simple like mirror. Very often it is a power. Okay, and one more related thing before coffee break. We can define something very similar, which is an order between games, and say that an actual game is lower or equal to another one. And it will be a partial order, that is very important. It will not be a total order, it will be a partial order relationship. We say that two games are equivalent, not when, we say that A is lower or equal than B as a game, not when they can be swapped in a sum without changing the result, but when they can be swapped in any sum in such a way that the result favors, B. If I say that B is larger or equal, so it's better for left, because left is the positive one. In any game, the result has to also be, when you do the swap in any sum, swapping actually favors left. Right? If that is the case, then this is the definition of A being great. Okay? The specific results are compared as this table. Right? So you can read, for example, as if in this sum, right always 1, well, it doesn't really matter, everything will work because anything is better for left than that. But if left was always winning, then swapping with B has to still make left always win, because otherwise this is not true. So this is what I am defining, the property that for any game sum at all, left will always like to swap A by B, right? Because the final result moves in the correct direction in a comparable way. 0 and star are not comparable. So if the result flips from first player wins to second player wins, that is not comparable. Something has changed and it's not clearly better for left, so that would mean that they are not lower or equal. But if the result does not change, or changes to basically something that is clearly better for left, when we swap A from B in all possible sums, then we say that this one. Right? And basically in the same way, and doing the same arguments, and doing the same mirror game, the proof is almost identical. Instead of I saying, and the games are identical and they still win by mirror, you basically still do that. I had a winning strategy here as left, I have a winning strategy here as left, I play both in parallel, and I will still win. That still is the main argument. So, by copying the same proof, actually the effective criterion is that you still just look at the result of the difference game, and that is your comparator. If the result of the different games, specifically that game, is a 0, the two games are equivalent. Swapping them never changes anything. If that one ends up being positive, I want to swap. I'm speaking of swapping A with B, so if I want to swap A with B, I should look at the result of B minus A. Right? This works exactly as if they were numbers, and I am swapping and updating the score. So if that result is positive, which we have, well, we actually have defined it as 1, right? It's positive. If that result happens to be left always wins, then the actual comparison is that A is lower than B. I mean, this will hold, but furthermore, they are not equivalent. For some game, there is an actual improvement. Right? Basically, it's easy to see that for the 0 game, there is an improvement. For the 0 game, it changes from yes, for the 0 games, it changes from second player to left acceptable. Okay, or for A, for some game, and vice versa. And the most interesting case is if the difference game happens to be first player wins, those two games are not comparable. There will be sums of games where it is better for left to swap A with B, and sums of games where it is not better for left to swap A with B. There actually be both, right? Which is quite surprising because, again, we only ever look at one single game to compare A and B, which is the difference, but that gives us a global conclusion among all games. Right? So it's a very common situation. Yeah. One very nice and simple but extremely useful corollary of this is that if you have a very complicated sum of games, but you have proved that each of the games individually is lower or equal to 0, so each of the games individually is either second player wins or left player always wins. In the addition, it will still be greater or equal than 0. Right? And as long as at least one of those was strictly positive, and they were not all second player win, the final sum will be left wins no matter. Right? So there are cases of not comparable, but this behaves as you expect. Positive with positive adds up to positive, negative with negative adds up to negative. Once you have non-comparable elements, well, crazy things can happen. And of course, the impartial games are all basically not comparable among themselves, right? They are only equal the one that they are equals, and other than that, they are incomparable, which makes sense because otherwise we would have like, oh, left prefers the star and star 3. And that makes no sense. The game is impartial. It should always be symmetric. Yes?
So if a lot of games are greater than equal to 0, and left goes second, left are what win, right?
Yes.
Okay.
There are a lot of proofs that look like that. I have to prove a greater or equal, and the proof starts. Okay, assume left goes seconds, we show it wins. If you go over the game theory, it's awesome because you have a lot of proof that are exactly like this. You got how it works. I want to prove this. Okay, start of the proof. We are playing the game, left goes seconds, and it starts with playing a game, right? But if you don't know about it, it's surprising because I want to prove like a mathematical formula and it starts, okay, I'm going to show that someone has tried. Yes, but I wanted to show like the general table situation. Like most of the things you want to prove of lower or equal, greater, you can simplify them to one specific, okay, in this specific game with such player to start, such thing to happen. Yes. Any other question? Was it answered? This was actually useful for analyzing the situation in problem G. The neonym, problem neonym. I'm not sure which one it was. But in that one, there is a very complicated situation where if you want to compute the actual game theoretic values are very complicated. But for most of the situations, the game favors one of the players a lot. So in your analysis at some points, using this kind of arguments, it's easy to say, oh, okay, all of these are positive. And so you end up getting like, okay, most of the positions I immediately know which player wins because individually, looking at each of those individually, I have already shown they are positive. And so the sum is still positive. Great, no more to prove. But the most complicated case in that one is the x equals 3 case. That is, the game actually has very, very wild values, but it can be analyzed. Okay, this is the most important thing. Yesterday there was not enough time to develop all of this. Now you have an introductory sense of how partisan games work. Right? One of the most powerful tools is looking at the difference game, basically, and it works as you expect. There's much more to read, and if you start working with specific games, you find out values and situations that are general, and so learning game theory values is useful. But again, the theory becomes much more complicated, and there's like no limit already. I think already for games that looks like this, so a number or the other player can move to something like this, two numbers, where x, y, and z are integers. So that would entail, after a very small backtracking fight of 2 steps, the game reduces to, okay, one of the players has such number of moves and the other has nothing to do. Right? Which if all the positions were like that, well, they are just numbers and yeah, that's the easy game. Already for a sum of games like this, it is, I think, piece-based complete and for sure NP hard to guess who will win very quickly. For the general case, it is uncontrolled, but you very often do not get a case like this. For many games, you have very specific values and you can. Okay, so let's go to the coffee break and then we'll have some more general concepts and problem discussion. continue. That is the best way to continue. So before completely dropping game theory, I see that there are many among you that really like very abstract mathematical crazy things. You were asking me about a very interesting question about game theory that makes a lot of sense. Again, if you're interested in this kind of topics, the Bible of game theory, so to speak, where to read more about this. There are still two books. There probably are more modern texts, but as far as I know, these are still the completely big, huge reference material. There's Winning Ways for Your Mathematical Plays, is the full name of the game, of the book. You will probably find it Winning Ways. This one was written by Conway and 3 other authors that I cannot remember. And on numbers and games, that is another book written by Conway alone. Basically, Conway wrote this one in a week or something like that, very, very quickly to publish it, and then with the 3 other companions, they wrote the huge book. So this one is probably easier to read. This one is written. I am pretty sure, because of how it is written, that Conway assumed this will be read by professional mathematicians that are interested in this topic. So it changes from very easy to read to you need to know a lot about ordinals and very abstract math. Very easy to read, you need to know a lot about it. So it changes. Some parts are very easy to read, some are very abstract. And this one is more consistent, like, okay, it has more pictures also, much more pictures. Then, as a curiosity, this is the table of some values as far as I could work out during the contest to solve this problem and actually solve it for the problem neonym. I was a bit surprised that it appeared in an actual ICPC contest, I think, because looking at the PDF, problem neonym seems to have appeared in a contest in Europe, and it's a very, very game theory partisan game. I guess you can guess for this particular game the situation, although it has a tricky case that you have to find by experimentation, sort of. Or I'm not sure how you would have the intuition, like there is a very tricky case here and how to find it. So you don't need game theory, but if you know a lot of theory, it will help. But it's unusual. I haven't found many problems like this. But this one is very recent. I think it's from December or something. I faced it in Universal Cup because they used it in Universal Cup, also recent. So neonym basically is a partisan game where left, as I am now defining who is the positive, right? Left is the one who actually is more powerful in this game intuitively. They are allowed to subtract. It's similar to nim, but in each heap, left is allowed to subtract any numbers from 2 up to k inclusive, and right is only allowed to subtract 1. So just by computation, you can do this table of values. This would be the nim heap size, and the columns have the k values, right? And luckily, like, we don't need to analyze more than k equals 4 because we can do enough reasoning. So basically, I have no idea, like for k equals 4, no, actually I think for all of those k equals 4, I more or less understand what these values are, but summing them would be very complicated, so I don't really understand the sum of these things, unlike this, which I know how to sum. But we don't care, luckily, because the conclusion is all of this ends up being positive and become clearly positive the more you go. So that's enough for our analysis. Because basically in this game, you can see that all the positions, like never ever in this game when you do the analysis does a positive number appear. Like the only numbers that actually appear are the -1. When you have heaps of size 1, those are basically terrible. Intuitively, you can understand that easily in this problem without game theory. If there's any one heap, a heap of size 1, left will lose necessarily, because basically only right can move there, and there are no other sizes in this game where only right can move there. Where only left can move, right? At every size, right has a move. -1 is always a legal move. So if there is any one, you can is the reason that there is a global strategy to win for right, which is simply subtract anywhere but here, reserve this move from the end, and if you haven't won already, and this is the only thing that remains, okay, make the move and win. Okay. But the reason, if you do the values, it makes sense why a -1 is enough to dominate everything. No other number, positive number, ever appears, right? For 2, we get this clearly. No matter the value k, left can move up to 0 to destroy the whole heap of size 2, but right could move up to -1. And these ones are games where clearly each of the players wants to play. You can imagine this is like a canonical decomposition of it. You can imagine that there is already a -1/2 in there, and there's a coupon for half an extra point, and whoever plays here gets the coupon. So if left plays first, it's -1/2 plus 1/2, it becomes 0. If the right plays, -1/2 minus 1/2, it becomes -1. So this has like an urgency of 1/2. You can get 1/2 point if you play here. And since everything that is above is basically very small and infinitesimal, this half dominates. Which also you can analyze by hand, because we already saw, okay, -1 is enough to win. If you get to this, the other will win, so any of these positions is urgent. And so actually when solving this by hand, even without knowing game theory, you can also reason sort of ad hoc for a neonym problem. Okay, I can special case handle heaps of size 1 and 2, so now all that remains are of size 3, and either left starts or right starts. That we will know, because maybe because of our analysis we had to make left play to avoid losing immediately, and now it is right turn. Okay. So what remains is to solve the positions 3 and above, right? For size 2, you can also do special case and notice that it actually becomes a pattern, basically. Right? For size 3, there are 2 interesting values in this table that, if you don't know anything of game theory, are not so obvious, but make a lot of sense from our analysis now, which are these 2 zeros, right? Because something is equivalent to 0 if it is a second player win. So actually, you can prove that you can, when k equals 3, which is the hardest case for this problem, you can ignore heaps of size 4 by playing heaps of size 4 by themselves and noticing that whoever plays loses when k equals 3. If left does -2, then right plays -1 and they will win because negative. If -3 directly played to negative, left loses. So left loses any move. And if if right moves, they will move to here, which is a positive number, whatever it is, but we can analyze it specifically. Like this one is positive because left always wins here, right? If left starts, they can erase everything, and if right starts, they will move here, but here, left can erase anything, and they win. So this one is for sure, regardless of how it is called, this is for sure some positive thing, and so we get to this one is a 0. So we for sure know that these things are positive, whatever they are, and these things are zeros, whatever they are, right? And for k equals 2, it is easy to argue that there is some reversible behavior, because both players have actually only one move on each heap in this case. So whoever player has a strategy assuming the value 1,3 can still do it by just assuming that that is the real actual value, and whenever the opponent makes a move, we also do a move, and that's a very common trick. I think there was another problem about trees and moving coins in a tree that has a very similar trick with modulo 2. Like anytime our opponent tries to move, we move again, and so only the even ones matter. Right? That's a common pattern. Here it is 1,3. So by a very similar reasoning, for at least k equals 4, the exact values are very complicated, but you can more or less easily prove that analyzing each one separately, like I am playing on a single heap of size x, they are all positive from size 3 on, right? It's not so easy to prove, it's not so hard to prove by induction, basically. Once you know that up to some point they are positive, you check your moves, and okay, they all go back to positive, so still left always wins. They play correct. And that is enough, because at that point you have already eliminated the only big things that appear and are critical and urgent, and so sum of positive is positive. In this case, we have enough to know that left player always wins. But k-equals 3, because of this 0 and this star, we are in a condition to prove that this is actually a star right now when k-equals 3, because well, the actual value is more or less complicated, but as an exercise, you now have an algorithm at least to prove that this is equivalent to the star. You would play this game plus the star, because the star is its own inverse, and verify that in that finite game, I mean, it's hard to do all the cases, but you can check, okay, in that specific game, second player can lose it, thus this is actually equivalent to the star. Right? Once checked, it's like, oh, okay, this looks a bit naive, but unfortunately, one won't go into the details, but some complicated infinitesimal but well-known values appear. So this, the specific case of k-equals 3, which happens to be the hardest, can be solved fully and is like a more or less standard situation in game theory, actually. It reduces to values which are sum of complicated but well-known things. Up is actually this very simple game. It has a name because it appears a lot. This one is positive because you easily check that left wins. And there is like a rule that if all you have are these tiny things, which are even smaller positive things, stars and ups, as long as you have at least 2 stars, left always wins. There is like this pattern that at least 2 is enough advantage. For less, well, you have to be more careful, but the rule is basically that if all you have is the positive one, it's still positive. And if there are stars, I mean, stars cancel by themselves. So if the parity ends up being odd, there is a star muddling the waters, and the situation is that once there is a star, if you don't have at least 2 ups, then it's basically a first player win. So up star is a first player win, but 2 up plus a star is already enough advantage that left will always win. Okay. So this is to me, I think this is the most, wow, I did not expect all of this theory to be useful in a problem case that I have seen in my life, but perhaps it never appears again ever. But yeah, this one surprisingly makes a lot of infinitesimal interesting values that are studied in game theory appear. You could special case it, but I think it is hard to notice that there is a very tricky special case here with the combination and of up and star if you don't study the theory before. I mean, some teams found it. I don't know. During the contest, it's funny that I actually made a bug in this table, and so I couldn't find it, and so I built a generator. And after seeing, oh, the generator said that this case is failing, I said, oh, but my table is wrong, and then I saw it. I don't know what to do. Like if you actually wrote a generator, that could be a way. Like you assume a simpler version, you have tracking brute force, you find a case where it doesn't behave, and you say, well, must be a special case, and you put some if, and this is a question for those of you who got accepted, like did you do something like that? How did you manage to do it? Or perhaps there's nobody here who solved it, and all of the table was from outside. Okay. I was actually not checking that, because I saw like 5 people who solved it. Then perhaps they were all outside contestants. If that is the case, it might be cheating, because they might have seen in the UCAP. I thought they were teams from here. Yes?
We could already have solved it yesterday, but was with a brute force generator and checking some if were missing. That.
I see.
In case with the cases that were missing were like having in cable 3, obviously, having one 2, some amount of 5, and some amount of 3. Like
1, 2. Oh, okay, that makes that after that first move, now it's the right turn. Okay, so for right start.
All the 3s and all the 5s.
All the 3s and all the 5, right. Then the parity of the 5s matter.
Yeah.
And if only you have 3 and no other things, right. If this number is even, then only the positive remains, and so it is positive because those cancel themselves by parity. And if this is odd, star muddles the waters and this becomes first player win.
Yeah,
So,
that
so
was
it is a special case.
that
It
was
makes a
tricky
lot of sense.
because we in the contest we saw that the fight behaves like something like NIM, and we said, oh yeah, we have an odd number of fives, a new number of five. Then we were like, okay, if we have five stuff that are not two, nor set,
Right.
nor six, we were like, okay, yeah, we have some like greedy,
Right.
but we forgot the three.
Right. Yeah, I can imagine. If you're not doing the actual values, it's not obvious. That would be special behaviors. For example, this one and this
Yeah.
one is very similar because by themselves they are both positive, but this one is infinitesimally smaller positive than this one, which is already infinitesimal. Yes, the precise distinction is very, it's very tricky to get.
We didn't make a
If you did
table.
it by generator, that I can understand totally. Yeah, it makes sense. That way, since luckily it's more or less a pattern guessable with many special cases, where you can end up finding the special case and trusting, okay, maybe there are a few special cases. Yeah. Nice to know. Any other commentary on this one? So yeah, this one was very hard. But it's the most, it's the closest to applying this part of game theory in a real context that I have been in my life. In a sense, I did apply to a real context, but I mean, it's not a qualifying contest or anything like that. It's important. This came from a qualifying contest somewhere. So it's all happy. I don't think this will become like mainstream like the NIM ones, because the NIM ones have a very nice theory and then you have big progress, and this is like too much. I don't know. Right? To me, like I really like one of the theory, so it will be okay, but I think it might be too much, too specific. Yes?
Also, when I saw the first time the problem, I tried to make all the table and the values.
Right, something like this. Yeah.
Yeah, but when I had to x equal to 2 and had the none, not the tip, the 0 minus 1,
Right.
I was like, what?
Yes, very quickly. I mean, you can get rid of this by special case analysis, but still, what remains for k equals 3, it's very tricky. Those are well-known infinitesimals, so if you
And
know
also-
them, you happen to be able to solve it, but those are very special. They're
Yeah, and
very
also
specific
when I see what was the x equal 3 with k equal 2, like I don't, in this moment I didn't have any tools for to manage to say, okay, when x equals 3, this is equivalent to 0. Like, I only have, okay, left has the 0 minus 1 and right minus 1. Pardon,
Right.
0. Just.
Yeah, the conclusion is that that's why it's very, very tricky. I think if like removing the k equals 3 case, this is within the normal problems that we see all the time. It becomes very tricky because of this case. Like if the setups were like, okay, from k at least 4, then suddenly it's a reasonable problem, or special case k equals 2, very usual problem you can reason about, and this one is unsurprisingly too. Anyway, let's move on. So that's enough game theory for now. Let's do a bit more general concepts and or problem discussion. I might want to mention two problems from yesterday. I think I would like to mention at the very least the one about critical cities, something like this. I think the name was critical cities. Right? There was a directed graph, I think. This one actually I am surprised because when I actually saw teams googling that yesterday, and I saw the same thing when I looked it up, and it's I don't know, it might be very well known, but I never learned it, right? And it seemed too complicated to me. So I think the question of solution for this one is too complicated in my opinion. Okay, so in this one we have two cities, A plus B. This actually appeared exactly as a practice problem in some IOI, I'm not sure which one, probably 2015, 16, something like that. So practice problem is like a work for this. So it must have already been well known. But the goal is to identify which cities are contained in every path from A to B. Right? There are many solutions, and I guess many of you solved it. But I saw that there is something I probably should learn it at some point, because it is a thing. There are things you have to learn. That's how it works. But I saw there is something called dominators and dominator tree. I officially say here I don't know what this is. I will have to learn it today. I have no idea what a dominator is. I assume it's not extremely hard, so I just have to read it, but I haven't. I am lazy. So there are dominator and there are dominator tree. I have no clue what this is. Did you use this for the solution? So many people use it. Because I googled the problem, let's see if it is well known. And I arrived at the end, I was like, this is super complicated. What's going on? Like I just saw a picture and I said, no, I'm closing. Not today. I will read it. It's probably equivalent to whatever I am going to tell now. But I feel like this is overkill. Like this is probably like some useful theory tree that will help in some other problems, but I think for this one it must be overkill. Like I don't say this is useless, this surely has useful properties, but I feel this one can be explained more easily. Okay, enough of backstory. How can we solve this one? Well, I will just mention how I thought about it, because now you can look up one solution with dominator tree, which my opinion is at least looks too hard. You have to build a tree, and that is already hard enough. I don't want to build this. So let's mention another way. So you can first run a very short DFS code to find any path, arbitrary path, from A to B. So let's say I don't know, this path. You have a global vector path, and once you find it, you start returning, and you do push back, so that you have the path. That will leave the path, let's say this node at X and Y. So that will leave B, Y, X, A pushed in the path. So it's reversed in the array. This will be 0, 1, 2, 3, the indices. But that ends up being convenient, because we then will try to do the path from the beginning, so it's like a stack. We will end up pushing it. So it happens to be convenient, otherwise. So okay, what is the first observation? We found any path. These are the only candidates, right? Because we are looking for nodes that appear in every path. So I choose a random path. Well, not random. I don't do an effort to choose a random path. I choose an arbitrary path, right? DFS, very short code. Once I have it, I just have to discard those that are not actually critical. So I will do a graph traversal. Actually, in my code, I do something like BFS, but with a stack, a vector with pushback, because why not? Like, I don't care the order. I just want to traverse the graph. With that very common pattern, have the bug of still not pending nodes to be processed, and while they are pending, process them. And if you have a neighbor unvisited, put it as a pending and visit, right? A very normal pattern. We want to traverse the graph. So here there will be no critical nodes, but we'll modify it a bit. So what do we want to do? We want to traverse the graph until we cannot progress anymore. Once we block, the idea is that we will block at a critical node. So initially, actually, we know that we need to start at A, otherwise we cannot make progress, and A will be our first critical, so we pop it, and it goes to the answer, it will be the first critical node. And so we put A in the queue, or the stack, or the whatever, the val, and everything starts. And so the process is simply that now we move to the neighbors, but we don't even need a separate value. We can just check the back of the vector, what is at the top. In my implementation, I put a -1 here, so that I never query the bottomless stack. Careful about it. So basically, we can only have the rule that I do not want to go to the next thing in the path. Why? Because I want to see if I can avoid the path. If I can sidestep the path and find some way in a different way, basically, I will be able to avoid it. But if I go through X, I am not avoiding the path, I am using the path, right? So the only rule to my graph traversal is that the only actual node to avoid is this one. The next one in the path. But with that rule, I start traversing. So I will be able to go to this node. I will be able to go to other nodes. And here, for example, something interesting happened. I can go to a node that is in the path, but it's not the forbidden one. It's not the first one. Right? This I have just a boolean of criticals, right, to know which one is critical and which one is not. When I can go to a critical node, that the ones in red, that is not the forbidden one, the next in the path, that very clearly means that, okay, I have the path, I am doing things, and I have arrived at someone which is not the first. And I have never touched the path before, so I managed to do some shortcuts and avoided using the path here. So none of these are good. Yeah. So what do? I just pop until this is I arrive at this node. And that is the new, might be the next critical candidate. And when I pop them, I immediately, they are reachable, because all of them are reachable from the very start. No check to do. So when I pop them, I also push them in my bag, right, and mark them as visible. So here I will arrive at the Y, X will be pushed, so my bag is like this, and I keep processing. And only when the bag processing stops and I cannot progress further, I know, okay, there was no way to avoid going through the next critical node. I pop it, I put it in the answer, and continue searching from there. Is that clear? Is it clear that?
I didn't understand how do you, like, once you erase like the X, how do you continue like looking for the Y and so on? Like,
The code for this part would be, okay, if I go to a neighbor, if my neighbor is critical but it's not the top of when the back is the vector, then I do while the back is not Y, pop and push it for later. Like X would be popped from the path. Like here, I will keep popping until I get I at the top. And everything that I popped, because I discovered those are not critical, I have managed to sidestep them. Not only do I pop them, I also push them into the bag for the search and mark them as visitors. Because I could have gone to them before, I only did not do that to avoid to avoid using the path. But it's like the path now is shorter. The path is always actually a path from some first node that could be the first critical to the end. And I keep reducing that until I block. When I block, I am completely sure, okay, this one I cannot avoid. I just pop it and restart the process. Okay, so the actual code is one DFS and one graph traversal with popping the.
is it a classical program?
To me, it was semi-classical. Like I knew it, I had seen it before. To me, this was like, this is the way this is solved, but I found that apparently it is very common to throw dominator tree at this. I'm pretty sure the tree has to do with this. It's probably something like, I would have to read it, but there has to be some relation between these values and the tree. But there is no tree here. At most, I have like steps. If we look at the algorithm that I am proposing, okay, there are the criticals, so my iterations would end up like first finding everything reachable in this first part, but then we get to a blocker, and once we restart the search, we will get everything reachable in this part, but then we get a blocker and so on. But this is like at most a path, like no tree in this version of the algorithm. Yes.
I have a question. How do you check that Y is not critical? You go.
The critical flag, when I found the path, I have a global array of booleans, initially all false, and I mark all of them to be critical. And that never changes.
Yes, but you discard X. Then how do
It's immediate. When I discard it, I also push it in the back and mark it as visited. I also have a visited mark. Like that is part of the graph traverse.
Yes, but
I never unset the critical flag because it doesn't matter ever anymore.
But my question is not with X, it's with Y.
Y is still critical. I will
Yes.
only, so it
But
keeps
how do you check that Y is not critical now?
it is critical.
Yes.
Why is the first critical?
It goes to B and then it traverses
Ah, for this particular example, you mean?
Yes.
Ah, okay. Well, right. In this particular example, I was at this node, so I found y. I would do all the pops, and this would be a new situation. From this node, I cannot conclude that I can sidestep them, but now this one can try to go this way, but that would also not be able to go past y. But when I process this node, right, which is still part of the search, at some point I will look at B. B is a critical node, right? Of course, it is in the stack. The definition of critical is it is in red, it is in the stack. Well, this one might have need to be red for consistency, but they are. Okay. So when I am here, I say, oh, B is critical, but it's not the top, so I need to pop, and then I will pop Y, B right now.
So you traverse the graph through all the nodes except for the ones that are in the path. So once you have no nodes on your queue left, for example, you know that the next node is critical.
Exactly. Yes. And then you basically put it in the bag and continue the search. But
Yes.
only when you do that movement from the top to the bag that you have enabled the next critical one, and so you can put it in the answer.
Okay.
Exactly. Yeah. I thought this was sort of known pattern, but apparently it's not that well known. I might have taught this to my students, but so my students know it, but maybe it's not so funny. I will later read Dominator 3, I promise. I will not today. Any question about this one? So I feel this one is very easy if you know the trick, and it might be hard to reason because it's also easy to conjecture wrong versions of this, like I do PFS and separate by distance. Those things can work, but you have to be more careful. I feel this is easier. Okay. Okay. Then let's move to completely separate thing because today is the general concept lecture, so I can speak about anything. No, not literally anything. We can cover like sequence of short topics instead of one long lesson. Okay. So I would like to mention a bit the Bell-Bamford algorithm. To me, at least, the way I think things, like most algorithms, there is some leeway in exactly what is the algorithm and what is not the algorithm. For many, there is like an official version, and this is the actual algorithm, and a slight variation is no longer the algorithm. But usually, we tend to say, oh, okay, anything like this looks more or less like this is life. Anything like looks more or less like this is so on. So Dijkstra and Prima are the same algorithm. They're friends, they go together. Okay. It all depends on how you use it. So, there's something about that with Bell-Bamford. To me, there is actually like one true version, which is not the most famous. And you should know the one true version and understand it well, because then all of the other ones follow, right? And you sometimes do not want all of the other ones. You want the one true version, right? Or some other variation of the one true version. So, first of all, do you know the Bell-Bamford algorithm for minimum path? Or not? We have mentioned it already. Who knows it? I guess most people. Yes, most people, but maybe not. Okay, it is quite a simple algorithm. How would you be able to write it by memory? Yes, I see you. Very, very trusted. So, I know that many people write it like this, essentially. Well, many times, let's say just n times, it probably should be n plus 1, but we can put 3n plus 1 times just in case. But it should be, this would actually be n times. So for every edge, so for a edge, or e edge in the graph, do the relaxation. Right? That basically means if A is an edge that goes from I to J and has a weight W, then we would do something like, okay, we could do distance Y plus the weight, and that would be a new candidate for the distance of J. So let's apply the old operator that does not exist anymore, replace it if it is that way. Okay, this is the full Bellman for analysis. Okay. This will be set dj to the minimum of its current value and this other thing. This used to compile like a million years ago, but it doesn't compile anymore in usual compilers. Anyway, so this is more or less the Bellman form. Do you know this? Right, we call Bellman form like this. I'm skipping the initialization, but it's the usual one, same as that, basically. 0 at the start, infinite at all the others. There are slight variations, of course. Well, what does Bellman form compute? Looking at it like this, you would think that it only computes distances, right? From one star to all the others. And the main advantage is that it's very short, and the second main advantage is that it handles negative, right? Okay. I guess, again, many of you, if not most, possibly, will, without any trouble, know what I think is the true version of the Bellman form, which is not this. This is like the crazy hack that happens to work and be used and be very fast and very well known. But the values that it is computing are very crazy, and it ends up working by sort of magic. The true Bellman form algorithm, I am sure the first thing that Bellman and Ford both thought, and then maybe they optimized, but for sure the first thing that they thought is I will just do dynamic programming. And because there are cycles and cycles make everything complicated, I want to break the cycles, right? Why? Because cycles and negative cycles make everything hard, especially negative cycles, but even if there are no negative cycles, the fact that I have cycles, even if everything was positive, so that I can use Dijkstra, still I need to use Dijkstra's algorithm, which is complicated compared to simple dynamic programming, right? The fact that there are cycles makes things harder. If there were no cycles, I could just do a simple recursion. So let's break the cycles. How can I avoid the cycles? Well, I can change my state. If my state is just where am I, well, of course, there could be cycles if the graph has cycles, and I cannot use simple dynamic programming. So this is the general trend, the pattern of thinking. I have cycles and that is not convenient, let's change my state so that there are no cycles. And the easy way that you can do that, and I'm sure Bellman thought about it, is okay, let's remember how many edges we have gone through. So it's not the same, I am here, than I am here and I have already walked 7 steps. Okay? With that notion, of course, you will never have cycles because you always increase when you move the number of steps. That is always increasing, and of cycles. It's impossible to go back to where you came. So that will be the actual state. How many steps I have used, right? How many edges have I traversed, and the actual node where I have arrived, right? So those are the values you would like to actually compute. It's called FLI to be the length of the minimum possible path for reaching node I with exactly L edges. Right? Well, and this is something that can be computed recursively very easy. I am sure you can do it. You would basically take the minimum of who was the predecessor, so for every possible edge, go into I with a certain weight W. Well, of course, you would check if J was the predecessor. I mean, I should probably just swap the letters so that it matches what I have on the left for convenience. So I would say I could go up to, this is now F. I could go up to node I and add W. And from all of the ways to do that, I take the best, because of course I can just brute force who was the previous node, right? I don't know who it is, I just brute force of the possibilities. Okay? And how, but I need to know what was the previous length, right, in terms of number of edges. What was the previous number of edges? Right, L minus 1. You're paying attention. That's very simple. One less edge, very clear. So this clearly works. It's elegant, clear, simple, no cycles. We can use dynamic programming. That's it. Right? Well, this is actually Bellman. This is the essence of Bellman. I guess this is not new for most of you, but it is very important to understand it well. Why? Because these are not equivalent. I mean, this naturally follows from this if you start doing some optimizations. Like the first and foremost optimization is, of course, just by looking at the code, dropping L, right? You can see an explicit L parameter here, no explicit L parameter here. Okay, someone dropped the L on the way. They made a bug, they had to say face, no, this actually worked, and they were lucky, it actually works. That might have been the story. So actually we can check the complexity. I mean, here there is a lot of implicit things, but you would basically now compute this using dynamic programming in the usual way, right? For every state, see the predecessors and compute compute that minimum. So actually, for every L, we would, for example, iterate all the nodes and add over the predecessor something. So it's basically for every L, we add up degrees, so it adds up to every edge. So it actually ends up being a total of n times m. I mean, actually in this version, we clearly can say L and be more specific, which is something nice. Here we were saying, what is the number of iterations? Here it is very clear, it's the length, whatever length you care about. If you only care about paths with 10 edges, then do 10 steps of this table, right? The 10 floors of this table, let's call it, the 10 levels of this table, and that will be enough for you, right? Whichever length you want to know about, when I say length, I mean, so we have length and cost in this case. Length would be how many edges, and cost would be the other thing what I am optimizing, right? So this would be the actual complexity. For minimum path, as long as there are no negative cycles, any minimum path is simple, and so has length at most n minus 1. So the complexity to use this for that case becomes n times n, the famous Bellman-Ford complexity, which is explicit in this version of the code. But we see that at least it matches, it will compute more or less the same in a different order. But this is more useful. You have to know this because it gives you much more information, right? I mean, yes, they are basically the same idea. This appears if you start optimizing this, and notice that if you do everything in place, crazy things will happen. You might converge to the values earlier, but you lose control of what each value means until the very end. At the very end, if there were no negative cycles, then, okay, finally you have the best possible path, right? But that's only at the very end. And if you wanted to control the length, the number of edges at any step, because that's useful for you, you don't have that at all. So you need to know this and have it very intuitive. So basically, you can always do this table fully from 0 up to n minus 1, which is the longest possible. So for example, just as an example to show the relationship between these, we might know as a recipe that, okay, we initialize the distances. That's like the table of length 0. Length 0 is without using edges. So for the starting node it will be 0, and for the rest it is impossible. The minimum distance is infinite. That's the classic initialization. The case of 0 edges, no. Just staying where you started. Then each of these steps, so will hopefully compute values that have something to do with at least one more row. Actually, and it's considering that if you iterate this k times, you will have the values of that dp at step k exactly. That is completely false. You get a crazy mix, which depends on the order of iteration. The only thing that you know is that you have values that are at least as good as that is. You get at least values as good as iteration k, right? But you don't have control of what are the values. So if you need any kind of detail on the values, it's better to do it separately and you have full control of what exactly every value means. So if you do it n times, which is the classic recipe, you can actually get paths up to n, right? And so for any, if you want to check for negative cycles, for example, the recipe is that if you check if the iteration n, right, the nth iteration, the one that would compute the values of length n, discovers any improvement, right? Because that should not happen if there are no negative cycles, right? If there are no negative cycles, all minimum paths are simple, they do not include cycles, or they can be made simple. So any path of length at least n has to have it's not simple, will have a cycle inside. So if one path of length n has improved any of the previous paths, then for sure you have a negative cycle, right? But if you wanted to, if you need to keep it separate and you want to reason it in a very orderly way so that you can control the length, because that might be helpful for you, what would be the corresponding step? Well, the actual values, I mean, if you know that there are no negative cycles and you want the minimum path, well, you know that the length in terms of edges is node n-1, so you could do only n-1 iteration. And then if this version controls very tightly and very conveniently exactly the number of edges, well, if you're not caring about that, for each node, its final distance would be the minimum across the whole column, right? Because you would like the minimum with 0 edges, with 1 edge, with 2 edges, you would not care. Right? You know that somewhere over there is the minimum. And for the same reason, there will be some negative cycle in the graph if and only if, when you look row n, you have somewhere at least one node such that the value with length n has improved the previous minimum, right? So suddenly using length n is better than all of the previous length, right? Is that clear? Might not be better than n-1 because maybe the optimal path has length 3, I don't know, and there is, so n happens to be better than n-1, but if there are no negative cycles, it will not be better than all of this. Some of this has to be the optimal. Is this idea clear? Any question? My main takeaway is you must for sure understand it very well, and there are many problems where this is much easier or even necessary, and doing it like this will not work because you need control of the values. That is very common, so it's worth to know it very well. Yes?
Isn't this table decreasing?
This table, I could not hear you, sorry.
Isn't it decreasing? Like,
no, not necessarily. I mean, it depends. There are variations on this idea. You could define this such that FLJ is the number, is the minimum cost of a path with at most L edges. Right? But I am defining it here, what I find more natural, to be the exact number of edges. Right? For the exact number of edges, these are not monotonous. No, not necessarily. Because, of course, you could have an excellent edge, which gives you a path of one edge that has cost only 1, but if you want exactly 2 steps, you have to pay a lot for that, right? But here, for that, if this is the start, and this is the node we are interested about, the value with exactly 1 edge will be 1. Well, this one is increasing, but perhaps there is over here another path, which is 2 to 2, I don't know. So this one with length 3 you will get 6, but with length 2 you will get 30, and with length 1 you will get 1. It's arbitrary, right? For the lower or equal version, which you can adapt slightly the calculation if you want, you basically accumulate a max minimum with what you had before to not lose it, essentially. In that version, yes, of course, because of the way it is defined, it becomes monotonous. I still find that this is the one that gives you like the full information. If you want the other ones, you can post-processing do a simple step on the table. For example, once you get the detailed information, if you only cared about lower or equal, that's like doing prefix a minimum over every column, for example, and so on. Like usually, you have the full information, and then you can get it. Yeah. Any question?
Yes. Why is it an if only if? Like the thing you said about the there is a negative cycle if and only if in the end column there is a value less than something in column.
Right. If there is a value that improves, that beats all of the previous one, right? Then for sure, there has to be a negative cycle, right? Because it means that this path beats all of the previous ones, and all of the simple paths are included in the previous ones, because n-1 is the maximum length of a simple path, a path without any cycle inside, without repeating nodes, right? So this beating all of the previous ones means that the minimum path is not simple. And that cannot happen unless there are negative cycles. And the other direction would be if there is a negative cycle, there will be some improvement here, right? That's basically
the
question.
Couldn't the negative cycle benefit in more than the nth layer? Like, couldn't it?
For this particular node, yes. But you can reason that if no node is improved at level n, then those, you could always be doing this version, and for the same reason that this version is correct, then this version will, if that will happen, this version has to be wrong, right? So that's an argument by authority. We know this one is correct, so it has to be correct. But what we should reason, for one node it is certainly false. That is a good observation, actually, because it could be a mistake. Just to check one node or think if this is the check for a specific node. Yes, because of non-monotonicity for one node, it could, there could be a negative cycle, and that node is becoming worse, right? That node could even not be part of a negative cycle, actually, and never improve. But for sure, if there is any negative cycle, some node has to improve at level n, right? I guess the argument is that you can you can start from the negative cycle, and there are slight details that I have not mentioned. If you use this code for a negative cycle, you usually initialize with zeros everywhere, and you want all the cycles to be reachable, right? If you have negative cycles which are not reachable from your start, depending on the details of how you check, you might never see them. Well, just make everything reachable so that you see them for sure, right? Once you know that, if you start from the negative cycle, okay, then for sure there is some path in the cycle, and if you start tracking it back, you will find that at step n it was somewhere, and that node will have to be less than. But I think it's to me it's easier to reason it like in terms of taking distances up to value n would be correct. Like twofold. The value that you will get if you take the minimum. So not this version. I think it's better if you think in terms of the other question that was, what if we, a variation of what if we do the code but taking lower or equal L as our distance. So we care about paths of lower or equal L. Well, then we will be reasoning about the minimum, right? It's essentially that version of the code. We could imagine that it is actually a post-processing, but all the time we will be looking at not the actual value, but the minimum of that value with the previous one, they call it. And it's easier to see that one of those has to improve if there is a negative cycle, right? That has to actually be the case. Why? Because if there is no improvement, those values do stabilize because of how the formula is. If there is a full row without improvement, because the formula is basically this same thing, but taking maximum with the previous one. In that case, if the whole row does not change, it will not change for the next level. So the fact that that one would stabilize implies that ours would stabilize too forever, but if there is any negative cycle, like every node that reaches it will at some point grow below bound, and then you have that, okay, but someone has to, that cannot happen, so someone has to have improved, and you will find it. Okay. It's a bit indirect, the reason. But I think the way to think of it is, if it was not the case somewhere, the values have become stable, and they cannot become stable with a negative cycle. So that's the intuition, at least to me. I guess you could write all the calculations carefully, but to me that is less clear than this stabilizing argument. But still, it is true. That is for sure. Yes. And that ends up justifying why it also works for this version of the code. Right? Because in the end, this version, it has crazy values in between. The invariant is less clear. It depends on the order. What values are computed at intermediate stages are not fixed, but they change depending on the order of the edges. So this one, that's why the only property it has is that it converges to the same values, basically. So since the only important thing we need to, in the end, decide for there are or not negative cycles is whether we can make the values converge or not, well, this one is actually checking that whether it manages to do an improvement or not. So that will also justify that this one ends up being correct.
Isn't it actually the same, like at step L, the left algorithm computes the same as the right algorithm if you change lower than or equal to L, I think. Like
No, because of this separation. Like, yours in place modifying the same array instead of having two. That is the source of the difference.
If you define it as not exactly L, not the length, but that length or lower.
Still, yeah, I mean, if you take this one, if you leave this code as is, but here you take also minimum of all of these, minimum that I already have, and the previous value, right? F, L minus 1, J, right? If you mean like this, what I was computing, and also the minimum with the previous value, right? If you do that, that still will not match the exact value that you have here. The source of the mismatch is that this is like, I have the previous row, I reserve a new row, and I do the computations outside. And this one modifies in place, which, depending on the order of the edges, can create a chain. Actually, for any graph, in this version, if you guess the correct order from closest from minimum distance to maximum distance, this is linear time. Because the first step correctly updates all the distance perfectly because it guessed the magical correct order. And then on the second iteration, if you want, it says, well, this one does all the same times, but there's also the usual optimization to check. If there is a full iteration without change, nothing will change or stop. So you could always finish in one step. Right? That's another way to notice this one actually cannot be computing the same values, because that one for sure will not check values ahead of its distance. And it's the source of that is the in place, right, modification. So this is not even equivalent to that version with the usual trick of doing everything mod 2, so that you modify the code as little as possible, right? For the full matrix, you only allocate 2 rows and then do modulo 2, the axis height. That still computes the correct, let's say, values in the sense that they are defined in this precise way. While this one computes something that is at least as good as that, and if you give them in a good order, I am already improving faster. Okay, so that's why reasoning about these exact values is almost impossible. If you need detailed reasoning, it is much better to do the actual table, or at least reason in terms of the actual table, and then if you want, justify, oh, I can avoid all of it, but this is much more tidy if you do it like that. Yes. In a sense, it's quite magical that the famous Bellman-Ford algorithm actually works, and even though it is stepping everything in place and doing everything very chaotically, still it works. Right? I mean, it makes sense, but It's not literally doing the same formula correctly, no, it's improving in random order. Any questions regarding this? It's more or less clear. Okay. So this will fall under the general concepts mainly. I mean, these would be graphs, but not okay. Okay, so to end, let's end on two general concepts to sum up, which appear in many problems. So this is very general. One concept that appears in lots of problems and we have already used and we will keep using, and so it is of course very useful, is to think in terms of, there are huge numbers of examples of this, we have used it already, think in terms of dominated elements. Oh, right here below it said dominators, so maybe they were dominated elements. It looks similar. You don't know what dominators are. These are dominated elements, they have nothing to do with dominated. Think in terms of dominated elements. With this equal. So this is such an abstract idea that it means nothing, as every good abstract idea should. Otherwise it's not abstract enough, it has meaning. I don't know why you're laughing, because that's true. So what is a dominated element? Let's appeal to common sense and your experience, especially. What would you say is a dominated?
It's an element that's completely useless for that.
Almost, yes, but in a specific way. It's not so abstract.
In any solution, you can find any other element which will be.
Okay, not any, but some.
Some.
Yes, yes, yes. Language matters. Yes, some other element. That's the key, basically. It's an element that you can ignore, remove, change, simplify, I mean, do something so that it's not as important as it was before. Usually it's just ignore it, because some other dominates it, right? Some other dominates it. And it is an extremely common pattern, which I'm sure you've used already, but many algorithms, I mean, sometimes it can be a slight optimization. You could even defeat, squeeze problems that should not get accepted, but the test cases are not very well done by some dominated element reduction. Like if you have random data usually has lots of easily to check dominated elements. I mean, for example, let's say you have points on the plane. How likely do you think it is that you will get a magical line of stairs like this, which might be relevant in your problem? That will not happen. If you get random points, you will get a random square. And in a random square, there is a point over here that dominates everybody. So if you delete them, you now have very few points, you solve the problem by this one, right? So I never said this in public, probably did. But if the test cases are badly done, it could be a constant optimization, not a worst case optimization, but it could pass. I have seen at least one example of this in the past. But that's why problem setters always check for solutions that eliminate dominated elements. But surprisingly, because this is not that surprising to me, but surprisingly there are also examples of algorithms that only work because you first eliminate dominated elements. And this would be one such example. Like this shape is very typical. There are many situations. I mean, first of all, I should mention the one-dimensional case, right? Because I have a two-dimensional case. But that one is quite obvious, so you usually notice. If you have many points, many times they are dominated by, let's say, the maximum. And so you can forget everything and just keep the maximum, right? That would be an actual example. Because of dominated elements, it is that so many of our algorithms just take a maximum of many things, because the maximum dominates all the others in some sense, right? That is obvious or extremely common. So the one-dimensional case we use all the time without noticing. Almost essentially any time that we take a maximum of many things, because the maximum is the important ones, it shows this pattern. But another very common example of that is the two-dimensional case, which I'm sure you have used before, where you have points, for example, and for some reason, when a point 1 has larger x, let's say, than a second point, and larger y than a second point, we can say that for the purposes of that problem, this one is better, and so we can ignore the second one. This specific pattern or things similar to that, these are extremely common. I'm sure you've used them. If not, you should pay a lot of attention, because this is a very common pattern. When you have this notion of dominance, the thing is that in the drawing, if you do the standard XY coordinate drawing, any element will dominate everything to the left and below, right? So an element like this will be dominating anything here, an element like this will be dominating anything here, and so on. So if there was in my set data an element like this, it would actually dominate this too. So it would actually ignore it, right? So you already see that dominated elements end up having some interesting structure. And that's a quite general pattern. Some algorithms, in some problems, it helps to remove dominated elements, because the final result has what you get once you eliminate the dominated ones has some interesting structure, and that helps in solving the problem. Many times you can do these eliminations and the final structure is useless. For example, with this pattern, it is very common, and you always get something like this. The final points that have not been eliminated because nobody dominates them, they all have this pattern that if you sort them by x, basically, so the x will be increasing, but then the y coordinate will be decreasing. Because otherwise, if you increase x and also y, you will get an element that dominates you. It should not be that. But for many problems, the fact that you have the points in this order is useless, right? So it doesn't become easier because you eliminate the problem. But this is a very common pattern. And this is only one example, right, of a common case that appears in many problems. But this thing in terms of dominating elements and remove them, it's a very general idea which can be applied even to more abstract things. I should actually say that elements is probably a bad word, because it already sets our expectations. It's not abstract enough. So we need a more abstract thing. What more abstract thing is there than a thing, right? A thing could be anything, even an abstract thing, right? Because an element sounds like something that is there in the inputs, or I create it, but it sounds like data. And these things might not even be data. It might be choices of what to do. If I have many choices of what to do, maybe some of the choices dominate the others, and I can remove the dominated choices. And they are not even data, they are abstract choices that I could make. So, right? And that's still another common pattern that you will see a lot. So it's useful to think in those terms. So what examples do you remember off the top of your head? Because there should be many, right? This appears for the time everywhere. Of dominated things, dominated choices, dominated elements. Perhaps in problems we did recently. This is a very open question. This one does not have an expected answer. Yes?
I've personally seen in Latin American regionals,
Uh-huh.
at least one problem about this, about dominated elements in 2D, about 1 or 2 per region, more or less.
Well, now that you mention it, it might be quite common.
Except the last 2, but the others had like, some had 3,
Especially this kind of pattern of taking the input data, eliminating dominate, and doing something because of the order that it implies, right?
Maintaining
You mean like that?
dominators.
Right. Right, or the dynamic version of this, which would be, okay, keep adding, but I only keep. Makes sense.
I've also seen like a lot of code forces problems with that idea. Like some educational problem that was really hard. It just did that, and there was a single sweep when in 1D.
Interesting. So the hard part was like to notice the dominance and how it
Like
helps.
originally it was a 2D problem,
Mhm.
so all the things, and it turned into 2D because of that.
I see. Right, because in the end, this behaves like a sorted array. Yeah, that is an interesting pattern. That's a good observation. That actually, this helps because in patterns like this, which are geometric, it can help reduce the dimension. That's another general concept, actually, the concept of relating sorting or data structures or sweep line or all of those ideas to the dimension reduction. It's extremely common that you do some kind of sweep lining, and the end result is a new problem that is more complex because it might be dynamic, it has changes, it has more structure, but 1D instead of 2D. So it's like a trade-off. You trade problem complexity of what you want to do by dimension. Okay, you have to do a more complicated thing, but in 1 dimension instead of 2, or in 2 dimensions instead of 3. I have seen those a lot. Also, problems in 3D that seems impossible, but in 2D they are at least hard managed. And the solution is a sweep plane, basically, right? Like you sort and now you reduce dimension. But that's also very common. Okay. So yes, there are many examples often. There are TMTC, too many to count, actually. But I would like to mention this idea of choices, right? Sometimes specifically, you have dominated choices. Actually, so what do I mean? You have a process where you have to do some choices, and it's sequential. I'm in an initial state. I pick some choice, do something, pick some choice, do something. The process continues, and I get to my final state. And I would like to do the best choices, right? So I might have many choices at some step. In terms of game theory, right? Today we were doing game theory. You can think of this as a backtracking or a minimax algorithm. Like I could be evaluating position as in a game engine, right? And all the possibilities of moves. But if I can somehow justify that some options are dominated, then it massively helps because I can prune the options, right? Backtracking. Pruning is basically applying dominated choices, like knowing that some choices I do not have to pursue because they are dominated. I mean, maybe the argument is not that some other choice dominates it. There's like a more global way to discard it, but I would think it's one of the most common ways to think about it. Like this element, there is like a binary relation. Like this element actually dominates this other. This choice actually dominates that. And there is a whole algorithmic technique that we use for problems, which in particular that one relies in a sense on dominated choices, like very heavily using the concept of dominated choice. Which one do you think I am talking about? Let's see if you agree with me, because it might be subject. Strategy stealing, well, okay, but that is too specific. But yes, it would be. It would be an example. Yeah. But that's also what something like more general. We use in many problems. Backtracking could be, yes, actually, if you take this to the extreme, if you prune and prune and prune your backtracking so well that you only have one choice because you prune the maximum possible, you get to greedy algorithm. So yeah, actually, this is the essential idea in greedy algorithm. You have to find so many dominated options that you have the one and good choice that dominates all the rest. There is no reason to do some other thing because if you always choose this option, you get to the solution and you will find a greedy algorithm. That's an excellent observation. And then finally, so this, I don't know, it might help. To me, these kind of relations, I feel that subconsciously help me with not limiting what I think on a problem and finding some problem, but it's harder to prove. I would have to do a study with hundreds of students, and so we will just have to go by feel. I think this helps. It's my method. Let's try. But there is one principle which I think is very interesting, and it's more subtle, which I call delayed choice. And this one I feel has helped me many times. I mean, actually, let's separate it into two, right? Dominated choices, we can actually say that a more restrictive choice is dominated by a less restrictive choice. Right? I don't know, let's just to invent an example. Let's say we have a problem, we have the actual problem of choosing the maximum sum of an array of values without choosing two consecutive. Right? Well, we already did some of this where some of the restriction, the choices that we could make were clearly less restrictive, and so we chose those instead of the more restrictive. For example, if the first three elements, let's put a very simple example just to show you. If the first three elements were the same, and I don't know, because of your problem, you know that that is true. It's just for the purpose of the example. Well, you could choose to use this element, but that forbids you to use all of this, and you achieved one element and 5 benefits, let's say. Or you could have chosen to use the one on the border, the array, and so that also gets you 5 of cost and of benefit, and it forbids to use this one. But now this one is enabled, right? So it is a subset. It's not a matter of quantity. I don't mean like greedy or heuristic argument. This one only blocks 2 options. This one blocks 3 options. So blocking 3 is worse. That might not always be the case, but this is much stronger. It is a subset. This one is blocking everything that this choice is blocking and more, right? It is more restricted. I have less liberty, so to speak, of what to do from for all the choices that will follow. If I do this, than if I do this. Is that clear what I mean? Okay, this pattern of what remains and a choice being more restrictive than another one is very common to appear in problems, and it's as a telltale that, okay, there might be some greedy here because it seems like there are some of these things happen. When you cannot clearly compare ever 2 choices and they all look like completely unrelated, well, it seems much harder to find some greedy structure too. And within this general idea of being more restrictive, there is a quite subtle idea that I have used many times, which is, I call it delayed choice. And the principle would be that delayed choice in general is less restrictive. So delayed choice is the one good option that you use, right? So what do I mean? Let's imagine, let's keep with this example. So let's imagine that I only gave you these 2 options. Either, even without looking at the values, either you right now decide whether to use the first element or not. Right? You have to decide it now. So your 2 options are basically use the first element, do not use the first element. But imagine that I also give you a third option, that is, you can decide later if to use the first element or not. Which of those 3 is less restricted? The third one, right? This is very obvious because this one already eliminates possibilities of sets to choose. This one already eliminates possibilities. The delayed choice of, okay, I will choose later, does not yet eliminate possibility. That is what I mean by delayed choice. So, a specific example of a problem where this can help, or a pattern where it can help. I feel that this helps in many problems. One specific example of this would be with intervals, right? There are many problems where you have to select intervals, as if it were a matching or something like that. You have to find the interval. They are not given. You have to choose the interval. And so, depending on which endpoint, which starting endpoint, which left endpoint you match with each right endpoint, there is some calculation of something of the problem that tells you the cost. And very often you have restrictions like, okay, you need to have k intervals or something like that, so you want to count, right? So, because many cost functions have properties that are good when we sort, I mean, at this point, I hope you have used sorting in many problems and noticed that if you sort and process in order, good things happen. Any sweep line kind of problem would have that structure. Very often you want to perhaps do some kind of dynamic programming that looks like, okay, I am in the process of looking at the points from left to right, and I am at point number I, and I have k intervals in some sets chosen or something like that, because I will in the end want to control that I need to have k intervals perhaps. Something like that. And I want to do something with the values. Well, if at each node I have to choose where to close its interval, very often this leads to an algorithm that works. Sometimes it doesn't, it depends on the details. Because maybe you need to store where you closed it and it has problems. But perhaps sometimes it does work, but the complexity becomes more complicated or goes out of control. It depends a bit. There are a lot of variation on this, because you would have to check where do you want to close the interval that you are opening here. So now you probably will need a second for that. And very often it's actually even worse than that. It's like you cannot even continue doing the problem because there are many restrictions between the intervals that you have to keep checking. And so if you put this interval, it's like you would need to control what you did with all of the middle intervals, and it's a very inconvenient moment to check. Like you would want to check it later when you are at those intermediate intervals, right? I hope you have felt something like this when solving some problem. This is a typical pattern. And this is a typical example of using the delayed choice concept. Okay, I am having a lot of trouble checking everything I have to check and doing everything I have to check because I'm trying to define. I am choosing to open this interval. Okay, it makes sense. I want to open something here, but controlling and choosing where to close it is giving me a lot of troubles. I have checks that I cannot enforce in a formula. I have costs that I cannot compute. I might have a for that is destroying the complexity. Brings problem. So this is a prototypical example of what I call delayed choice. You don't need to. You can delay that choice basically. The same idea exactly as this. You are not forced to choose right now where to close it. Right here it was this is just a conceptual example because the algorithm might not use it. But here it is very helpful to say, okay, I don't need to right now choose where I will close this interval. I can do it later, right? I can only choose that I have opened an interval here, and it's like open, right? So my state, when I arrive later at this point, might be like, okay, I have 3 open intervals that have been opened before and are still hanging over there, and I have to close at some point, but I haven't chosen anything what to do with them. And it's very common, this pattern, that if choosing where to close brings you a lot of trouble, you delay that choice. Okay, that's not my point. I will decide that later. It fixes all of your problems. You probably have to change the state, what it means, or some detail. But very often it leads to code that works, instead of code that you cannot make work. Or sometimes it helps with complexity. But I think it's even more common that it becomes possible to solve the problem, and before the formula did not even give a correct recursion. Is the idea clear of what I mean? There was actually one of the problems in the contest. I think in one of the first contests, perhaps the very first one, I think, it might even be from the first one. That uses this one. You happen to You have an idea of which one, maybe? I mean, there are like 60 programs, so I wouldn't know if I were. But I know that a few of you have an incredible memory, so maybe some of you will remember. There is some subjectivity also to this, right? Because there might be multiple subjects. Well, I think grid completion problem is a problem where this helps a lot. At least to me, it helped me a lot. Because in that one, you can, I think actually the best way to think about this problem is to think of it like you are building two independent matchings in a big graph, one that has letters A and one that has letters B. So if you draw the big it's like, okay, you would like to select what you are doing from top to bottom so that you can process it. So if you rotate it 90 degrees, now it's like this drawing, but because people drawn like this, we have to go up to down. So you have this kind of situation. Oh, this one needs 1A to solve it. So it will go backwards, it will go forwards, and it's very hard to decide what to do, which will be the matching A that has to go with this node. So the patterns fits perfectly. You actually want to decide, okay, this one will match with someone in the future. Okay, my state will keep track. I have 7 A's floating, right? When I'm here, it's like I have 7, when I reach this node, maybe I have 7 A's floating that comes from above, and okay, I need to do something with them, but I will delay what I don't need to decide it now. So if you think of the problem this way, to me it becomes solvable. I needed to be able to solve. But it is quite a general principle. Like, if it makes sense for your problem to change the order of how you set up so that that choice is done later, very often that helps, because as a general principle, of course, it's less restricted, right? It gives you more liberty to choose at the last possible point what to do, right? I feel that interval problems lead very naturally to this, because you have this, you turn this open and close two decisions in one situation to split it into two decisions. Okay, I open it, but then the closing is delayed. We will later decide that I close it. Usually this is fruitful when you don't care too much about the identity of the elements that you open. Like, all of those are more or less the same when you have to close. That would lead to this working as is, like without modification. Like perhaps if not, you have to have extra care. But if that is the case, this works direct, very direct. Is it clear more or less what I mean with these patterns? Okay. Any question? Any other example? This is just maybe nobody has an answer, because I am not expecting an answer. This is a genuine question. Do you remember some other pattern that you want to share, or any idea regarding, example, I wanted to say, sorry, regarding delayed choice? You think, oh, I have used something like this in such situation.
Similar variant,
Like this
really,
one,
but you can like regret the choice you made and do it.
Okay. It's like the negative version. Like you don't postpone the decision, like you do it, but it's a provisional decision. In a sense, it is delayed because you put it there, but if you later are allowed to take it back, the final decision is delayed. You still are delayed the final decision. But that's a good pattern. Yes, sometimes because of calculations of bookkeeping, it might be easier to do the decision and then just have the option to modify. We could say that the Chu-Liu algorithm, the Edmonds algorithm of the cycle was something like that. It was like, oh, okay, I decide to use the cycle, but that is provisional because it is wrong. It won't be able to use the cycle. But provisionally, I just use the cycle, and later it discovers, oh no, actually I do the swap. Right? So it could be thought of as an example of that. Like, take a decision that I can later adapt to find the correct final decision. Yes, that makes sense. It is very similar. Okay, I think we are on time, so it's a good moment to talk. Thank you everyone for listening to the talks. I hope they were helpful for you. To all of those competing soon, relatively soon in Santiago at the Latin American Championship, well, a lot of good luck for you. I have not seen any of the problems at all, so this time I have no idea of anything. I hope they are very nice and you enjoy them. And the same for me. I hope they are very nice and I enjoy them. That we will see. I have high expectations, like they will be great, but no real idea. So yeah, good luck to all of you. Let's go.